Finite element analysis of variable thickness disc wheel rim for weight optimization. Abstract: the objective of this paper is to introduce lightweight wheel rim by opting variable wall thickness of wheel disc without affecting its key functions and life. Wheel rim 3D model prepared in Pro-E software. Linear static structural analysis of wheel rim were performed in FEM, ANSYS software to determine stress level at various loading conditions, given boundary conditions to optimize disc thickness, weight, cost of wheel rim. The results of the FIA analysis to validate with the experimental test results. Keywords: wheel rim disc, variable thickness, Pro-E design, FIA. Introduction. A wheel rim is a highly stressed component in an automobile that is subjected to bending and torsional loads. Since it is subjected to high stresses and demand of long life, light in weight, which it becomes very important to select right material and manufacturing process in rim design. There are competitions among materials and manufacturing processes due to cost, performance and weight. The main components of the wheels and tire system aggregates is the wheel rim. Performance of wheel rim directly affects the vehicle performance and safety. Wheel rim size selection is based on tire size used in vehicle. It has standard catalog, JOTMA, which recommends standard wheel rim size accordingly. TATA 1109 ILCV vehicle recommended wheel rim size is 6.5 x 20 is as per JOTMA's standard for 8.25 R20-14 PR tire size. Wheel rim was taken for weight optimization analysis and experimental study purpose. Refer below. 3-piece wheel rim figure number 1. In this perspective, expecting wheel rim design with significant mass reduction without compromise in its function and performance. The above wheel rim weight can be reduced by recognizing various stress regions and corresponding changes in wheel rim design. Rim material can be removed wherever is lower stress region and has low vehicle load effect. 2. Problem statement. Currently TATA 1109 ILCV vehicles recommended wheel rim size has higher weight, cost, which need to be analyzed and optimized under finite element analysis. Analysis of wheel rim to determine the material removal area, changes in von Mises stresses and deformation for current and modified rim design within given boundary condition to gain significant advantages for lighter mass vehicle wheels. 3. Methodology. The methodology involves technology for performing the designing and analyzing of the object. Design and modeling of 3-piece wheel rim. Dimension specification. Analysis by ANSYS. Analysis to perform at various load condition on existing and modified rim design. Analysis of wheel rim under boundary condition to obtain deformation and von Mises stresses of model. Obtained optimized wheel rim and compare with existing model. 4. CAD design. Design input parameters of TATA 1109 ILCV vehicle. Existing 3-piece wheel rim design. Vehicle tire size, 8.25 R20, 14 PR. Wheel rim mass per wheel, 42.5 kilograms. Recommended wheel rim as per IDOC, 6.5 x 20. Load on each wheel, rated and overload condition, 2,300 kilograms, 2,650 kilograms, 3,000 kilograms. Material, rim RST37 and disc, YST38. Wheel rim disc manufacturing process, press forming. Mass of vehicle, 3,960 kilograms. Payload on vehicle, 8,710 kilograms. Existing wheel rim CAD design prepared using Pro-E software. Sketcher. Part design. Assembly design. Wireframe and surface design. Meshing and analysis by ANSYS software. V optimization scope. 3-piece wheel rim optimization scope, design. The following are the design changes incorporated to reduce the wheel rim weight, cost, and improve its performance. Increase in nave thickness to avoid crack initiation in the region due to fretting. Variable disc thickness to reduce weight and cost of rim. Increased cold working effect on the product. Optimized brake drum clearance through variable thickness. Wheel rim flow forming manufacturing process. 2. 3-piece wheel rim optimization scope process. The goal is to flow form and optimize disc weight. Increase disc material yield strength. Process compress disc material to increase its hardening by cold working, hence we can get higher yield, tensile strength, and thinner thickness. Reduce the rim weight without compromising the performance. 6. Optimized CAD design. Modified 3-piece wheel rim design. As per above table number 2 and figure number 4 where wheel rim design changes and process improvement were done for optimization, CAD data has been modified in Pro-E. Optimized wheel rim design proposal made based on finite element analysis, FIA. Wheel disc thickness increased at the region identified to have higher stress and gradual reduction of material thickness at lower stressed regions. The modification in the design is shown in the Fig 5 and 6. Following design changes to be incorporated to reduce rim weight and also simultaneously improve its performance. Increase in nave thickness to avoid crack initiation in the region due to fretting. Variable disc thickness to reduce weight, cost of the product and new process of variable disc increased cold working effect on the product. Improvement in brake drum clearances. Adaptation of rim flow forming manufacture process. Flange shape optimization. 7. Analysis. TATA 1109 ILCV wheel rim specification 6.5x20 design and modeled in 3D using Pro-E software. 3D model imported to ANSYS workbench for further analysis such as cornering effect through FIA and compare stress analysis at different loading condition. Geometry of 3-piece wheel rim. Boundary condition. Wheel, adapter, bolts modeled, assembled. Tetrahedral mesh used for the wheel and hub. Cornering load applied. Rim flange fixed in all DOF. Results viewed in the post-processor. Meshing and boundary condition for wheel rim. Meshing and boundary condition applied in ANSYS. To reduce degree of freedom from infinite to finite with the help of discretization or meshing, nodes and elements. Wheel rim flange were fixed and cornering load applied. Wheel rim stress distribution and analysis. The wheels were loaded due to cornering and lateral effect and same was simulated at various test conditions and accordingly results are obtained. FIA evaluated displacement at each node of wheels according to the initial boundary conditions from which the strain can be calculated and then using Hooke's law the stress at that point can be calculated using the Young's modulus of the material of the wheel. Equivalent stress results 10b. Fig 10, a. Stress plot with uniform thickness wheel disc at 30 knots. Fig 10, b. Stress plot with variable thickness wheel disc at 30 knots. 8 results. The following table number 5 shows comparative stress analysis results of existing as well as modified 3-piece wheel rim design with various load cases and boundary conditions. Comparative stress analysis results. 9. Summary. The FIA comparative results shown in table number 5 that the variable thickness disc had lower or equivalent stresses value as than existing wheel rim with uniform thickness. Analysis shows the uniform thickness disc had a stress value of 170 MPa whereas the variable thickness disc wheel had a stress value of 162 MPa. Peak stresses at the vent hole region for existing wheel rim with the thickness of 11 mm. By introducing variable thickness about 10 mm at same location the stress level can be brought down to 5%. Variable disc thickness achievable with an advanced manufacturing technique called the flow form/spinning process. This process facilitated the vent hole position in a single plane with adequate ventilation area and the reduction in stresses was also noticed. With modified wheel rim design weight is reduced from 42.4 kg to 36 kg per wheel, which is approximately 16% without affecting functional requirement.